So yesterday we were talking about these tables here and how they're interpreted. So as we said before, when we talk about buckling, I'll take this as an example. So when we talk about buckling, we've got a beam here or a column. I stick a load on and then I gradually increase it, and then suddenly as you increase the load, suddenly it buckles. So we start with the axial force, gradually increase the load, and you can see suddenly it buckles. So the sudden buckle occurs at this Euler load, which is pi squared EI over L squared, and that's also known as the elastic critical load. And a beam, a column, or a beam column can't take any more load than the theoretical Euler load, pi squared EI over L squared. So that was for that case there, which you can see. I'll now quickly switch over to here, and we'll just try and explain the same things again. So here we've got the pin-ended case. That's going to be buckling at pi squared EI over L squared. So when that load reaches pi squared EI over L squared, suddenly everything goes off to infinity. Remember, here I'm actually applying a displacement, I'm not applying a force. So if I was applying a force, as soon as it reaches the buckle load, everything would shoot off to infinity. Deflections, stresses, everything. So a beam or a beam column or a column cannot take an axial force more than pi squared EI over L squared. It's theoretically impossible. So moving from here to here, and what's happened in moving from there to there is that we have changed the boundary conditions. So this one is roller, so these two ends are rollers, and then this end is a pin, and then this end is fixed. And as a result of changing the boundary conditions, compared with this case here, we're saying that the Euler load increases by a factor of 2.05, which is exactly the number that you're reading off in your course book. So just recap, push that's pi squared EI over L squared, and then just push that onto the buckling load, and that would be 2.05 times pi squared EI over the total length squared. So that would be the total length squared. So let's just rewrite that. That's pi squared EI over L squared, and then this one here would be 2.05 times pi squared EI over L squared. So note that I'm saying L, I'm not saying L effective, I'm saying the actual length. The actual length is L, the actual length is L. So this one would be pi squared EI over the actual length squared, and this one would be 2.05 pi squared EI over the actual length squared. So what we'll be doing in a second is just having a look at the proof as to how to get the 2.05. You're not going to be examined on the how to prove the 2.05, but it's just generally a good idea for engineers to know where that number comes from, so that if you're ever asked in the future, you know the background to that. So when we do that, we'll be going to be coming along. Well, after we've done that, we're going to be talking about a few other things. One of them is this concept of the effective length. So we would say that this one is pi squared EI over L effective squared, and in this case here the effective length is 1, because the effective length is the actual buckle length, or L effective is the half sine wavelength. So when we apply that, the effective length is the same as the buckled length or the half sine wave length, and so whether it's LEFF squared or L squared, it doesn't make any difference. This one we would also say is pi squared EI over the L effective squared, or the effective length. So remember, this time we just get a buckled shape that we can see, and we can see that the effective length may not actually be the actual length of the beam column. So in this case here, that pi squared EI over L squared would be the same as the effective length, or we could say the effective length factor is 1 because L effective and L are the same. But in this case here, because of the change of boundary condition, another way to look at it is to say that the effective length has reduced. So the effective length is now theoretically taken as 0.7 of the actual length. So if the actual length was 1, then you'll be putting 1 meter, you'll be putting 0.7 into the calculation for the effective length, because you've got a different boundary condition. And then here we would say if the effective length is 1, and the actual length is also 1, and so both of these would be the same. So when engineers think about these things, there's two ways to think about it. One of them is through an effective length concept, and the other way is to think of it through the changes to the pi squared EI over L squared, that this one here is 2.05 times larger. So generally, well, both ways are completely consistent, so you'll be able to convert from here to here quite easily. But generally, when engineers talk, we're talking in terms of effective length. So when an engineer looks at a beam column, one of the first questions they would say is, what is the effective length? And that normally can end up with being quite a long debate between engineers. So just have a look at these other examples again. So in this case here, the actual length, if we were looking at this problem here, we would say, and we wanted to use the effective length concept in this one here. When we apply there, we will see that this one buckles into 2 sine waves, and so the effective length is that distance there, or that distance there, which in this case turns out to be the same. So in this case here, when an engineer says what is the effective length of this beam column with a support that doesn't allow movement in that direction there, and the effective length of this situation is that distance, or the same as that one there. And when an engineer says what is the effective length of this case here, where this one, say, is, where if you pretend that was 1 meter, let's just pretend that is 2 meters, and you apply your force through here for the buckle, the effective length, or the half sine wave length in this case, is 2. So in this problem here, you would use an effective length of 2. In this case here, because of the restraint, you would use an effective length of 1 in your calculation, and you would end, in this case here, you would end, or an effective length of 1 meter here. In this one here, you would use an effective length of 1 meter, and in this one here, you would use an effective length of 0.7. So that in that way, we can relate everything back to the effective length calculation, pi squared EI over L squared. And once you know what the effective length is, you just drop it into these equations here. So in this case, the effective length is 2. In this case here, the effective length is 1. And then from there, you will get the buckled load. And then in the last case that we talked about yesterday, the effective length of this one here, so you would say, what is the effective length of this one here? And the effective length of this one here is going to be 0.5, half of 1 meter, half of this length. And all of these numbers for the effective length can be calculated theoretically. So what we'll do now is we'll just look at the solution, at the theoretical solution to determine that value of 2.05. And once you've got the 2.05, you can turn that quite happily into the 0.7 as we talked about yesterday. So back to here. For engineers, this is quite a normal table to be looking at. the 2.05 and the 0.7 can be related to each other quite easily. And you can see the 4 and the 0.5 there, and you can see the effective length is the actual length for that case. So in this one here, find the critical load and the buckled shape for a column with one end fixed and the other end pinned. So in this case here, we will have you'll have your column or the beam column like there. One end would be on a roller, so we'll draw the roller like that. And then you've got your load coming down in that direction, so we'll call that your load P, and the other end instead is going to be fixed. So let's see if we can draw the deflected shape. So we would know the deflected shape would look something like that when it's stable under the load. So we would draw a deflected shape that would look something like that. So you can see there's been a rotation that's been allowed there, and then it would come back in down there, and then there, as you would already know, that would be 90 degrees. So from here, you got your P coming down there, so you would know there's a P going down there. You would also know that there's going to be a moment reaction at that point there, which we'll call MA. We also know that there's going to be a reaction there, which is going to be RA, which we'll call RA, and we know that there needs to be an equal and opposite reaction coming out there, which is going to be RB. So we know these two are equal and opposite, and then we know that this MA is going to be equal to 0, because RB multiplied by the total length here, L, is going to be equal to your RA, and that's going to be equal to RA, which is, RA multiplied by the actual length. Okay, so that's taking moment equilibrium. From there we get RB L is equal to MA is equal to RA multiplied by L. Okay, so what we do first is that we'll try and take the free body diagram, just so that we can set up the boundary conditions. So with the free body diagram, we'll just make a fictitious cut somewhere along there, exactly what we did with this case here. And with the free body diagram, I'll try and draw that out there, and then we'll put this thing here. So now we've got the load P coming down through there. We've got our load P, we've got the axial force coming through P there. We've still got that MA, which we've now calculated to be RA times L. So RA times L, and then through up here, we've got so here we've got our RA coming down there, and then for equilibrium on this side here, we've also got RA. And then down here, again for equilibrium, we're going to have a moment at that point, and that moment is going to be, the bending moment there is going to be a function of x. And while we're at it, let's set up our conditions. X there as 0 going up to the total length, and then here that would be a distance x. That would be our distance x away from the supports. So after we've done that, we now write out our equation. So the equation that we'll be writing out would be the sum of the moments at the cut. So remember, that's the cut, and that's going to be equal to 0. And then from there we will get 0, taking our moments, is going to be equal to P multiplied by V plus RA times X minus RA times L minus MX. And that's going to be equal to PV minus RA L minus X plus the bending stiffness EI V double dash. And then if we rearrange this, we're going to get EI V double dash plus PV is going to be equal to RA times L minus X. And then from there, we'll get V double dash plus P over EI multiplied by V. And that's going to be equal to RA over EI L minus X. Okay, so that's just from the free body diagram. I'm taking the moment around the cut, and I'm taking the sum of the moments around the cut must be equal to 0 for moment equilibrium. And then we would say let alpha squared equal to P over EI. Okay, and that's about as far as we want to go. So that's just setting up the conditions. So that's almost exactly the same as what we did here for this case here, but instead we've got a slightly more complicated condition with there being a fixed support at the bottom. But apart from that, the process is almost exactly the same. So we'll stop there. So we've got the equation, and now we'll jump onto Quincy's solution for the mathematics. So we've got this equation there, which is a differential equation of the form V double dash plus alpha squared V is equal to RA alpha squared P L minus X. So this is a non-homogeneous second order differential equation, ordinary differential equation. So we would know from our mathematics this consists of a complementary function and of a particular integral. So the complementary solution relates to V double dash alpha squared V equals 0. And we know from before that we would expect the complementary function to be a sine function. We can deduce it anyway by looking at the deflected shapes, because they would all form sine functions as before. So this bit is exactly the same as what we did for the simply supported case like there, where it buckled like there. So complementary function VCF. We can now guess some values, effectively just putting in the boundary conditions. So we set the boundary conditions, and then we re-express in this simpler form, equate the coefficients, and then we get VPI. For the particular integral is RA over P L minus X. The total solution is therefore this, the complementary function plus the particular integral, and now we put it through the boundary conditions. So the boundary conditions, as we had before, here the deflection is 0 right at the support, and when V is equal to L, it's also 0. And then we've also got the gradient here, it's 0, or the gradient or the rotation here is 0 because of the fixed support. So you shove those into here, and then you can solve for your B's, and then you can solve for your A's. And then you get this equation here, 0 equals RAP alpha sine alpha L minus RAL P cosine VL, and then that all goes to 0. And you then end up with this equation here. Okay, so we'll end up with that equation there, which can then be related to tan alpha L equals alpha L. So just go back to what we're trying to achieve through all this. We're just trying to achieve or to demonstrate where this 2.05 comes from. So I'll show that to you in a second. So having gone through all the maths, we are now left with an equation which is going to allow us to solve or to get that value of 2.05 with these boundary conditions, and that's going to be tan alpha L is equal to alpha L. So we need to be able to solve that equation there. Okay, so just imagine, like, if you had any problems with that, just imagine you're asking to solve tan x is going to be equal to x, and then what values of x would tan x be equal to x. So let's now let's just have a look at a graph that I've plotted. So from now on, just forget about Quincy's solution, because I'd rather just show how it can be solved graphically. So here we've got an equation, and then this is your tan function. So we would all recognize that as being the tan function. So these are your tan functions. So this curve here would be the tan of alpha L, or if you prefer, just call alpha L as being x. So this axis here is going to be x, and this axis here is going to be tan of alpha L. Okay, so we now want to solve the equation. So here are your tan functions, which we can see there, and this line here represents alpha L. So this line here represents alpha L. Okay. So we've got alpha L here, so obviously that line is at 45 degrees if the axis here and here are the same. And all we're trying to do from this equation, tan alpha L equals alpha L, is to find the interceptions, or where the graph of alpha L intercepts with the tan alpha L equations. So what we would then do is that we would, you can draw your graph out, and if you had a bit of graph paper, and then if you were able to just read off that value. So I've also done this in an Excel spreadsheet for you, where I've put in the functions. Please remember that we're doing everything in terms of radians. Sorry, I didn't remember. So I didn't mention that before, but please remember that the tan function is all in terms of radians. And so when we read off this value here down here, that value where the intercept is going to be, i.e. where the tan alpha L intercepts the value of alpha L, that value is going to be equivalent to 4.493. So I'm quite happy for you just to be able to read that off from a piece of graph paper, 4.493. So that is the solution. Tan alpha L is equal to L when alpha L is equal to 4.493. And as before, of course, there are other solutions. There's another solution at that point which could also be read off by the graph paper. So if you plotted it, you would be able to find all of the solutions. But as before, we're only interested in the lowest solution, which in this case turns out to be 4.493. So having done that, back to here. So just ignore all of this part here, because I'm saying that we want to be able to solve that graphically, and there's no need to use Newton-Raphson or anything else. It can just be read off on a sheet of graph paper. So now substitute that back into alpha squared is equal to P of EI. So we've now solved what the alpha is, 4.493. So we've now solved for that. So plug that back into this expression here, and it now becomes PCR. So we get 1.43 pi over L squared. And then from there, we get this 2.056 pi squared EI over L squared. So that number there is approximately 2.05, and that's where that number comes in. So you can see that this equation, 2.05 pi squared EI over the whole length squared, is where the 2.05 comes from. So theoretically, we've shown that the elastic critical buckling load of a of a beam column, one end fixed and the other end pinned, is 2.05 pi squared EI over the total length squared. Okay, so that completes example 1. So now we come on to how do we relate the 2.05 to the 0.7 for this effective length concept that we want to talk about, which is the same as how do we relate that to there, or that to there, or the 0.25 to there, or the 0.25 to 2, or the 1, or this to here, which is the same. The effective length is the actual length. So this is here where this concept comes in. So examination of the formulas for the critical load show that they can all be expressed as PCR pi squared EI over L squared, where we've got this 1 over eta, where this eta is some numerical value depending on the support conditions. So this eta, this term up here, which we're now calling 1 over eta squared, relates to the boundary or the support conditions of your beam column. So eta is some numerical value. So rearranging this equation, pi squared EI over eta L squared, which is the form that we want it all to take, so that that portion there is just the same as what we have for the simpler case. So we get pi squared EI over L squared, where L effective, or this effective length vernacular that we're talking about, is equal to eta, which is an effective length factor multiplied by the effective length. So we will see here that for this case here, the effective length is 0.7, or the factor is 0.7 multiplied by the actual length. So the effective length, if L was 1, is going to be 0.7 meters. So 1 meter and 0.7 meters. So note that the last formula for the critical load is the same as the pin-ended beam, with the effective length replacing the actual length. So that's what I explained at the start of the lecture. And the effective length can be understood as the length of a pin-ended column which has the same critical load. And this is now shown in this example here. So here we're saying if we had the effective length, and the effective length, if we've got this condition, this support conditions here, where that is the total length of the beam column, because the boundary conditions are fixed and pin, we would say that the effective length is 0.7 of the actual length, and then here we would show the effective length. So the effective length is the same as 0.7 times the actual length. So we've got the effective length as 0.7 of the actual length, or the effective length factor, or this eta, is going to be this 0.7. So this explains how you then relate the same elastic critical buckling load to an effective length of 0.7, so that we can all use exactly the same same equation, so the same original Euler equation, and it's just a case of changing the effective length factor. Right. Okay, so that explains this terminology called effective length. There's now another terminology which we're going to be talking about, and that is going to be called slenderness. So we said before in our discussions when we set the model that only slender columns or long columns are going to be prone to buckle. We now want to be able to define what this term slenderness is. So let's say we've got, well, we know we can calculate stress. So we've been able to calculate this PCR, which is a load in kilonewtons at which your beam column is going to buckle. Of course, you can turn that into a stress just by dividing it by the cross-sectional area of the beam column. So we've got we then have a sigma CR is equal to the elastic critical buckling load. Just remember that's P Euler pi squared EI over L squared. Divide by A, and then we get this term or a stress. So we've converted our load in kilonewtons at which it buckles into a stress. So from there, we put pi squared EI over L effective squared, recognizing now that we're thinking in terms of effective lengths, so that everything can be related back to the same expression. And then we've divided it by the area, and then we can see that our stress has now got an I over A. Okay, so pi squared EI over L squared, and then the A is there. Now, we're going to be calling this ratio here, I over A, is known as the radius of gyration. So going back to Civil 210, there's a concept now called the radius of gyration, which just expresses how far or how the cross-section has been is distributed around the neutral axis in its average sense. Thus, how big the sectional second moment of area is relative to the area or the amount of material that we need to use. In other words, for two cross-sections with equal A, so we've got two cross-sections here. This one here is a solid cross-section, and this one here is two circular ones with it being hollow inside. In this case here, both of them have the same A, but this one here would have the larger radius of gyration. So this one is going to be illustrated in the next example. We know that this one here is going to be called the radius of gyration, so I over A, and you know what radius of gyration is from Civil 210, and it's just the I over A square rooted, and that's known as the radius of gyration. So radius of gyration. So rewriting this expression down here, substituting the radius of gyration in, we just simplify that to be pi squared E radius of gyration squared divided by L effective squared. Simplify that a bit further, and we get pi squared E over L effective over R, the whole thing being squared, and then we come up with this definition of lambda. So slenderness is lambda. Okay, so slenderness is lambda, and there we have this thing called slenderness. So from this equation, we can see that the stress at which buckling occurs is inversely proportional to the square of lambda. So remember this lambda, it's similar to L effective, but it's just L effective divided by R. So if you say what is the slenderness, you say what is my effective length first in meters, and then divide that by the radius of gyration. Units of radius of gyration are also meters, and then out would pop a value of lambda, which is known as the slenderness. So a slenderness describes how easily a member buckles. On the other hand, loosely speaking, the ratio of length to the lateral dimension is also an applicable intuitive measure of slenderness. So slenderness is a bit more abstract, but it's related to the length. It's related to the length of the member, taking into account the distribution of material, which we can see there. Okay, so we now know what effective length is, and we know how to use it in the equation. Just basically looking up your boundary conditions or your support conditions, and that would give you an effective length that you can read off. And we now know what this slenderness is, lambda, which is just the effective length divided by the radius of gyration, or some measure of the material of your section. Okay, everything that we've talked about up to now has been for a theoretical column. So we've been able to we're assuming that we're calculating the stress, or we're calculating P Euler, at which the column becomes unstable. But that's a theoretical column with perfect support conditions. We're assuming that these theoretical columns, they're perfectly straight. There's no crookedness. We're completely ignoring the material properties apart from the Young's modulus. So we're completely ignoring how the material behaves in terms of what load it can take before it fractures. And we're assuming that the load is being applied exactly directly concentrically right through the centroid of the section. So everything has been very idealized up to now. Idealizations are fine. They can be useful, but once you have an idealization, you now want to turn this into a design model. So you want to be able to use this theory that we've developed of P Euler to be able to relate that to how we can actually design a column in a real building. So here we have our theoretically perfect columns here. Now let's talk about imperfect support conditions. So observing the results in table 2, which we referred to before, in table 2, just looking at these values here, with fixed supports having larger critical loads in the columns of the same length with hinges of 3. In reality, it's difficult to ensure perfect conditions, and some rotation would occur at the end, or something would happen. So because of all of these problems, imperfect support conditions, the fact that the column is not perfectly straight to start with, the fact that the load actually comes off at with an eccentricity, the fact that the stress strain curve or the fact that there is material nonlinearities, and the fact that you've got non-slender columns, we now need to be able to find a way in order to use that. So in practice, it is difficult to model exactly such partial flexibility at the supports. So the design standards, including our New Zealand standards, relate this back to how it can be used. So that's imperfect support conditions, and this is initial length of straightness, which is another of the conditions. So when we produce or cast a column or a steel column, the columns are not perfectly plumb. There is an initial deflection. There may be some curvature or some imperfection, and there may also be some residual stresses that have been locked in as a result of the cooling process. So the columns are not initially straight. So how do we take that into account? We take that into account in this expression here. So we've got an expression here, EIV double dash, is equal to EI v double dash x is equal to the bending moment as a function of x. So that's where we had it before. So let's just go back a few pages and we can see that that was the expression that we had up here. EI v double dash x is equal to minus mx for our perfect column. Now we've still got this bit here, which is the v of x, but now we're going to see if we can develop some theory where we can introduce v naught x, and we're assuming that this is the initial imperfection. So we say that the column is not perfectly straight and there's a very small imperfection, so sometimes that imperfection is about L over 1,000, so 1,000th of the actual length of the column is the initial imperfection. And note here that we're assuming that the initial imperfection is also a sine function. So rearranging this, rearranging that, we using the alpha squared equals p of ei as before, we obtain this equation here, and which is a non-homogeneous differential equation, and the general solution is the complementary solution and the particular solution. We know that the complementary solution is going to be something that involves the sinusoidal functions a and b. The particular solution depends on the initial imperfection, and to be able to process this, as I've just said, we're going to assume that the initial imperfection, or the equation that describes the lack of straightness or the initial imperfection, is taken from a sine function. So to be able to proceed, we will assume that the initial forms a half sine wave, which in any case is a good approximation of the typically encountered initial deflections. So we've got this v naught x, and we're assuming that the v naught x is a sine function. So a is the amplitude of the imperfection, and then just so that it matches, it would have to be sine pi x over L. So we can just check that when x is equal to 0, the sine of 0 is 0. When x is equal to L, then that becomes 1, and sine of pi is 0. So the initial imperfection would be following this this shape, with the magnitude at the center being your A. So when A is the deflection at mid-height, which we've just shown there, so the particular solution is then here, and then B is a constant to be determined by inserting equation 22 into equation 19, and doing so leads to this equation here. And then the general solution for this problem, starting off with the initial imperfection, becomes VC plus VP. It's equal to this. Now, applying the boundary conditions for the pin-pin columns, pin at the ends, V naught equals naught, which leads to B equals naught, and V of L is equal to naught. So that's pin up there is A sine alpha L equals naught. So applying the initial initial boundary conditions for the pin-pin columns. Equation 25 is obvious, but equation 26 requires a bit more consideration. So the particular solution then becomes infinity for the non-trivial case, and because of that we're forced to assume that A is equal to 0. So given that the general solution is going to be in this form here, rearranging it into this form here, the total deflection, i.e. the initial deflection, which we would see there, can be written as this function here. So V naught, V total of x, which is the total displacement, is equal to V of x relative to the initial deformed shape, and that comes out quite nicely as V naught x 1 over P over PCR. And if you're wondering, just here is the proof that V naught x P over PCR minus 1. So that's just the proof that that one ends up in terms of that side being that side there. So you don't need to worry about the proof. We just now need to worry about this equation that we've been able to develop. So in this equation, P is the load that's being applied. PCR is of course pi squared EI over L squared. So we can see that when the axial force P that's been applied there, when the axial force P is equal to PCR, then when P is equal to PCR, you've got 1 minus 1, and then your deflection goes to infinity, because anything divided by 0 is infinity. And then up here is your V0x, which we have said before that your V0x is going to be a sine function having an initial amplitude of A. So consider the mid-height additional deflection denoted by this delta. So that would be this this delta, the delta here as the Vx. So delta is the deflection at mid-height, is equal to V as a function of L over 2. So substituting L over 2 back into these equations here comes out again with this A, which is the initial outer straightness, divided by PCR over P minus 1. So we're now showing a plot of this in this graph here. So this graph here shows P over PCR. Remember, when P over PCR is equal to 1, deflections and everything shoots up to infinity, which is exactly what you can see here. And then on this axis here, we're showing delta over A, or the ratio of delta over A, which is the magnitude, of the initial imperfection. So it can be seen that as the axial load P increases, so does the deflection. So that would be that graph, that case there, and then that one here would be the delta at mid-height. So as you increase your load, your deflection at mid-height increases, and then when your load gets nearer and nearer to the pi squared EI over L squared, you would expect your column to become unstable and it can't take any more load, and that the column will be destroyed before reaching the critical load for the initially straight column. And that leads us on to example 2, which we'll go on to next time, which is just really how to use this equation here to predict what the deflection of the column would be at a load ratio, or with an axial load, which you've divided by the elastic critical buckling load. So we'll stop there, and then we'll come back later on after the break and continue with example 2.